Now we're going to talk about logistic regression. When the response variable is a dichotomous response, that is a response with only two choices like yes, no, A, B, up, down, true, false, etc., we can use something called logistic regression to model the outcome. Dichotomous responses are categorical. Dichotomous responses can be re-expressed in terms of the responses 0 and 1 to make them quantitative instead of categorical. Using this re-expression, samples of dichotomous response data can be analyzed. Before we go on, we need to define something called the odds of success. You may have heard people toss around the term odds in place of the word probability, but to statisticians, these are two different things. The odds put the probability on a different scale. The odds of success are going to be the probability of success, that is P, divided by the probability of a failure, 1 minus P. We're going to denote the odds by the Greek letter theta. So theta equals P over 1 minus P. The odds go from 0 to infinity, while probabilities go from 0 to 1. So let's imagine a couple of these. Take, for instance, a probability of 0.5 in the middle of our left-hand column. How do you compute the odds? Well, it's P over 1 minus P. So P here is 0.5, and 1 minus P is also 0.5, and 0.5 divided by 0.5 is 1. So that's how we arrive at 1 on the right side. Take the next set right here. If your success probability is 0.9, and theta equals P over 1 minus P, and your success probability is 0.9, then your failure probability is 0.1, and 0.9 divided by 0.1 is 9. So the odds are 9. So as you can see, as you get below a half in your success probability, the odds get very, very tiny. And as you get above a half, they get very, very big, very fast. Okay, so we have an example. In a study of esophageal cancer, scientists collected data on the size of the tumor in centimeters and whether or not it had spread, what's called metastasized, to the lymph nodes for 31 patients with esophageal cancer. The data are displayed in the plot to the right. So what we did was we coded the data instead of saying, yes, the tumor metastasized, or no, it didn't metastasize. We said 1 if it metastasized and 0 if it did not. So can you see a pattern in this data? I do. I think that larger tumor sizes appear to metastasize more often. Notice that the smaller tumor sizes tend not to metastasize, and the larger tumor sizes tend to metastasize. So can we use a simple linear regression to model this data? Does fitting a straight line do a good job of modeling this relationship? Well, as you can clearly see from the picture, it does not do a good job of modeling the relationship. Furthermore, what would our predictions mean? What is 0.5 tumor metastasis? That has no meaning. Okay, so another idea is to split tumor size into categories, small, medium, and large, to do a chi-square test using a contingency table. Tumor size category versus metastasis. Notice we would lose information. Our data has a much more refined predictor, that is, tumor size is a continuous random variable that we can predict from. So we're going to use logistic regression. And logistic regression attempts to predict a binary outcome from a continuous predictor with a sigmoidal or S-shaped curve. So we want to predict the probability of tumor metastasis, or the odds. Let's start with a model that we know, beta naught plus beta 1x. Recall, it predicts Y, tumor metastasis, but this has no interpretable meaning. What is a half of a tumor metastasis? For instance, tumor metastasis is a binary outcome. So we're going to predict the log odds of success in the following way. The log of the odds, that is log of P over 1 minus P, equals beta naught plus beta 1x. So the right side looks familiar to us. That looks like our simple linear regression model, but the left side is different. So the estimation of the parameters in this model is not the same as it is for simple linear regression. The specifics of the method are beyond the scope of this course. We're going to let computers do the computations for us. So when we do logistic regression, we're going to want to put things back on the odds scale rather than log odds. It's bad enough that we can't talk in probabilities a lot of the time, that we have to talk in odds, but it's even worse to talk in log odds. So what we're going to do is we're going to exponentiate both sides of the log odds equation. So something that I need to mention is that in statistics, we frequently use log to denote the natural log. And I know that is really strange for those of you who have a pure math background and don't have a statistics background, but that is the way that it goes for statistics. You will see that happen all the time. So we're going to take e to both sides. So we've got e to the log of the odds, e to the log of p over 1 minus p on the left, and on the right we have e to the beta naught plus beta 1x. Now, the e to the ln undoes itself, so we're just left with the odds on the left side, p over 1 minus p, and on the right side, we still have e to the beta naught plus beta 1x. So this is looking a little bit better. Now we can get something in terms of the odds rather than the log odds. But let's go ahead and take it one step further and put this in terms of the probability. Well, we can do that. It just takes a little bit of algebra. So let's let y equal the ugly looking thing on the right, e to the beta naught plus beta 1x. Then we have the odds equals y. So p over 1 minus p equals y. Now remember that we want to get p by itself. So I'm going to take both sides times that denominator so that I have p of x on the left and y times 1 minus p of x on the right. And then I'm just going to distribute the y on the right-hand side. So p of x equals y minus y times px. And then I'm going to take the terms with the p of x, all of them over to the left. So I add a y times p of x to both sides, and I have p of x plus y times p of x on the left and y on the right. And I want to get p by itself, so I'm going to factor it out of the left side. So I get p of x times the quantity 1 minus y equals y still on the right side. And then I'm just going to divide both sides by 1 plus y. So once you know the odds, you can change it back into the probabilities and vice versa. So the last thing we need to do is put back in our expression for y that we started with at the top. And we have that the probability is e to the beta naught plus beta 1x divided by 1 plus e to the beta naught plus beta 1x. It looks kind of ugly, but we'll get used to working with it. At least it makes our interpretations nice in terms of probabilities rather than odds or log odds. Now, we have one more result that we want to get to so that we can start using these things to make some good interpretations. We're going to simplify the odds at x plus 1 relative to the odds at x. The reason for this is going to become clear when we get the result, so let's just go ahead and get started. So we're going to start with the odds at x plus 1 divided by the odds at x. Now what are the odds? That was e to the beta naught plus beta 1x, right? We just did that a minute ago. So in the numerator, we're going to put x plus 1 in for x, and in the denominator, we just have plain old x. Now, because of the rules of exponents, I can distribute the beta 1 in the numerator through the parentheses. That was the first step. And the right-hand side of this equality here is just using the rules of exponents. Because I have one base and 3 things added, I can separate those out, all having the same base. So I took e to the beta naught plus beta 1x times e to the beta 1 in the numerator and still kept my denominator the same. And of course, the e to the beta naught plus beta 1x cancels out then in the numerator and denominator, and I'm just left with e to the beta 1. So the odds at x plus 1 relative to the odds at x is just e to the beta 1. So let's review for a minute our important results that we've gotten so far. We started with the log odds equaling beta naught plus beta 1x. And we want to remember that the log in statistics frequently means the natural log. So I just want to remind you of that. And you need to start getting used to looking at that, because when you get into higher level stats books and blogs on the internet, you will often see that done. So keep it in mind. We also have that the odds p of x over 1 minus p of x equals e to the beta naught plus beta 1x. That was just getting rid of that log odds and making it in terms of the odds. And the next step was making it in terms of the probability of success. And we put that as e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. I gave you another way to look at that on the right that has a little bit less computation. That's just dividing everything through by e to the beta naught plus beta 1x. And you get that equation. You can just use the one on the left, that's fine. And last but not least, the way that the odds change at x plus 1 relative to x is e to the beta 1. So we're going to use these results in our example. So we've got our logistic regression output out of a computer package called Minitab. And I've gone ahead and I've added the logistic regression, the equation for the probabilities onto the picture. We'll talk about that in just a second. But first, let's talk about how to read the output. So the intercept is the same as it always has been, B naught. And the tumor size coefficient is 0.5117, and that's what we call B1. So just the same kind of looking output so far. And then what we are modeling here, that curve on our picture, that S-shaped curve, is the estimated probabilities of tumor metastasis. So and remember, we just derived that equation. It's e to the b naught plus b1x divided by 1 plus e to the b naught plus b1x. Of course, we had betas in it a minute ago, but now we're dealing with our sample estimates. So let's use this logistic regression to get an estimate of the probability of metastasis at a tumor size of 7 centimeters. So how did we get estimates of things before? Well, we just plug in our x. So we're going to plug in 7 into our model, and we'll get that the probability, our estimated probability, is e to the negative 2.0858, our b naught, plus b1 times x, 0.5117 times our x of 7, and plug those numbers in the denominator, and you get 0.817. And that corresponds to what we see on the picture, right? So if you had a tumor size of 7 over here on the picture, you'd go up to the line and over here on the right, and we're about right, 0.8 or so. So now we need to interpret this, and that is an estimate that a tumor that is 7 centimeters has an 81.7% chance of metastasizing. So it's an estimated probability or a percent chance of occurring. So now we're going to use it to estimate and interpret how the odds of metastasis change with tumor size. So remember how our odds of metastasis change along with our x? That was that theta x plus 1 over theta of x. So that ended up being e to the b1. It was e to the beta 1, but we have our sample estimates. So e to the b1 is e to the 0.5117, which turns out to be 1.67. Now, this is the odds of metastasis at x plus 1 relative to x. And what is x here? It's tumor size. So it's the odds of metastasis at the next tumor size relative to the previous one. So let's go ahead and interpret that. With each 1 centimeter increase in tumor size, odds of metastasis are 1.67 times the odds previously. Now, the logistic regression with one predictor can be generalized to more than one predictor. Your equations look basically the same, but you've got more coefficients and predictors, just like it was in multiple regression. And just make sure when you make interpretations that they are after holding all the other variables in the model constant, just like we did in multiple linear regression. And you'll be able to practice these in your homework.